in 20.2 modeling and density. And what we're really doing here is working with measurements that have two different units. In this case, one above the other. And what I mean by that is often number of something per something else. So the classic example that you see everywhere is, the signs when driving down the road. You're studying for your driver's test. You know that, say, the speed limit in the state of Alaska is 65 miles, okay, per hour. Means every 65 miles, it should take you 1 hour, right? So you can simplify this equation. 65 divided by 1 is just 65. And then you can put m, or miles, over h for hour. So 65 miles per hour. We're essentially taking the number of miles we travel every divided by the number of hours we travel. This is just my example. In geometry, all of our equations here are going to involve some kind of area or volume or something like that. So we won't do miles per hour problems. Those are algebra problems. But the functionality and the manipulation of units is the same. So we'll do some examples here. The first one is density. So regular old chemical density is defined as the mass of something divided by the volume. So in this case, mass may be something like, say, grams, right? For those of you doing chemistry, or kilograms. If you're an imperialist, you might say pounds. It would be, or what's another good mass? Like tons. A ton of something. And then the bottom unit here is some kind of volume. So in this case, we could do grams per milliliter, or kilograms, pounds. Another good one for pounds is like gallons, maybe. Gallons. Other units besides these that are kind of relatively specific for volume, sorry, I got some light in my face, are cubic units, right? So every ton per, say, cubic yard or something like that. So in this case, it would be yard cubed, or in kilograms per, say, like, what is that? Cubic meter or something like that. Cubic meter. So all of these would be valid examples of density. There is no one set unit for density. It's some kind of mass variable over some kind of volume variable. So all of these would work. It just depends on what's going on. The example they use in the book for the first two are types of wood. So we have to compare these two types of wood and see which one is more dense. The downside is they give us the mass, but they do not give us the volume. So here's the mass, but there is no volume here. We have to remember that this is, it says that these are logs, right? So they're cylinders. So here's my little cylinder, right? It's just like a little chunk of tree. And the formula for a cylinder, should be reviewed here, is pi r squared, right? The area of the base, and then times the height. Gives us the height, it gives us the diameter, which helps us get the radius, and then we can go from there. So I'll go ahead and work my way through this without too much talking here. But I would, if I was to redo this problem, I would make a new table. I would just say type of fir, Douglas fir, American redwood. I'm going to make a new table here with a nice straight line. The first category is going to be the radius. The radius of this first one is 3. Radius of the second one is 4, right? Half the diameter. And the height is 17. We'll keep that in there. 17. Height of this one is 12. Notice that the units are the same here, so I don't have to convert. They're both centimeters. And then this gives me the volume is going to be r squared times h times pi, which I'll just grab a calculator and we can do that. So let's see, r squared, so that's 3 squared times the height, which is 17, times pi equals, I get 480 for the volume of the first one. 480. We can sure say 0.6 or 0.7 or something. 7. Remember the units for volume in this case, since we had centimeters and then we squared them and then we had another centimeters, that's cubic centimeters, right? But I won't put the units on here just for space reasons. The other one, r squared. Let's see, so that's 4 times 4 squared. I could have hit the squared button. Times h, which is 12. And then finally times pi equals 603.18. The book has to make a prediction, but it's a little weird. The volume is more dependent on the radius because that's what you're squaring, right? So it's more important to be wide. That'll give you bigger volume than a little bit higher. Sorry, what was that number? 603.2. 603.2. And then finally, I can put the mass down here, but I'm just going to skip ahead to the density. The density mass per volume. So in the first case, it's 254. 254 divided by my 480.7. That's equal to 0.528. So let me grab something new. 0.528, and I'm going to put units on this one. It's kilograms per cubic centimeter. Okay, and it makes sense you get a pretty low number. A cubic centimeter is pretty tiny. It's like that big or so. So you wouldn't expect it to be super heavy. In fact, half a kilogram seems like a lot for a cubic centimeter, but say let me. Let me do my other one. Other one had a mass of 271. So 271 divided by 603.2 equals 0.449. 0.449. Again, this is kilograms per cubic centimeter. So therefore, when it asks to determine which one is denser, we can say that, oh, Douglas fir is more dense, right? Because it has a greater density. If you mix up this fraction and you do, say, volume divided by mass, you'll get the other one. So just be careful of that. One other way we can do this is we can talk about the population size or the population density of something. And essentially, the formula here, it's really pretty simple. I'll write it here. It is things per area. So my dad worked for Fish and Game, so they'd go out and count moose or something. So they'd be like moose per, say, square mile. So that would be their units there. And they wouldn't just pick, 1 square mile. They'd pick like a survey area of 100 miles. And if they go into a 100-mile area, right, or 100 square miles, and they count, say, I don't know, say 80 moose. That means that they have 80 moose every 100 square miles, right? This is moose per square mile. Moose per square mile. So that's equal to basically 8 divided by 100, or 0.8. 0.8 moose per square mile. So just something to think about there. We'll do the example here. Burlington, Vermont has an area of about 160 kilometers and a population of 109,000 people. What's the approximate population density of Burlington? Sometimes they'll make it a little harder to figure out the area, but you have to use an area formula for some shape. But in this case, again, it's just things per area. So we do 109,000 per area, which is 160. Mr. Calculator says that 109,000 divided by 160 is equal to 681.25. And again, people are like, oh, you can't have a quarter of a person, but it's just a density, right? It doesn't mean that you're chopping up people. It's just on average, how many people are in an area. So that gives us equals 681.25, and the units on that, right, are people, the thing, per area. So in this case, the area is square kilometers, which you can do is like that, kilometers squared. So that would be your population density. All right, that's it. Have a good day.